Okay, ladies and gentlemen, in this video, we will be doing something entirely new, and this is really useful. We are going to learn how to find the area underneath a curved line. Okay, so a curved line, it will slope up, and we want to find that area underneath the curve using something called an integral. And this is really an easy technique with an extremely powerful result. Let's take a look at an example of how we might use this in the wild, in the real world. Let's clear the work surface here and get started. Let's say that we have our function. This is example. Let's say we have the function f of x equals x squared. Okay, if we graph that function, just a sketch, this is what it looks like. Starts at the origin point and it goes up to the left like this and to the right about like that. Okay, not an exact graph, but it gets the point across. Now, the idea with an integral is to find out what the area is underneath the curve, particularly over a specified distance. So let me explain the problem we want to solve. I want to know what the area is underneath this curved line, which is actually would be impossible to do with any degree of accuracy, um, with perfect accuracy, if you were just trying to measure it somehow, because the line is constantly curving, and as we saw in the video on derivatives, since the line is constantly curving, the area underneath it is constantly changing. So what if I wanted to know the area under the curve from 0 to 6? Well, what that would look like, the thing I'm trying to find is this shaded region right here. Let me shade this region in here with this green. So I want to find out what this green area is right here. And once you see the area that we're trying to find, you can see why it would be somewhat difficult to find it using like a ruler or um, a traditional area formula. We don't have like area formulas for curved lines like this. We have them for some types of curved shapes like circles and cones and cylinders, but what about this curved line right here and over that specific distance? So I want to know what is that area right there? What is that? And it's actually not that hard to figure it out. Remember, when we take the derivative of a function, let's just take the derivative of this function, f prime of x. We bring down the 2 in front of the x, and then you'll have 2x raised to the, and then we subtract 1 from the exponent. So the derivative of this function is 2x. And that helps us find the slope of the line as it changes. So this is what the derivative can help us do. The derivative helps us find slope. Derivative finds the slope. But that's not what we're interested in here. We're interested in the integral. So an integral symbol looks like this. It kind of looks like the F hole on a violin. If you've ever seen a violin, it's got that weird little F hole on either side. and that is actually the symbol for an integral. And what we want to find is the integral from 0 to 6 of our function f of x. All right, so how exactly do we do that? Well, what we do is we kind of do the opposite of what we did with the derivative. So again, let's put x squared here so and see what we need to do. So we have to kind of go in reverse from what we did before. So before I subtracted 1 from this exponent, now I'm going to add 1 to this exponent. So before I subtracted 1, now I'm going to add 1. And before, when I subtracted 1 from the exponent, I brought the original exponent down here. Okay, so instead of doing that, I'm going to think 2 plus 1 is 3. So if I were to have brought a 3 down here, what would I then need to divide out in order to arrive back at x squared? And it makes more sense when you just look at it. So I would need to divide by 3. Okay? So the integral equals, so the integral from 0 to 6 of f of x is equal to x cubed over 3. And if that's a little bit confusing to you, let me show you how you can get back from your integral to your original function. Integrals and derivatives are, this is called the integral. Now, this little dx here is something we'll talk about in a later video. To get back from the integral to a derivative, you just have to take the derivative of the integral. So now we'll take f prime of x cubed over 3. Okay, and f prime of x cubed over 3 is equal to, now bring down the 3, 3x, 3 minus 1 in the exponent section leaves behind 2 over 3. And now these 3's cancel, leaving behind just x squared. So if we take the derivative of our integral, you arrive back at your original function. Okay, so you see how these things interrelate. So in order to find out what that area is, let's get back to our integral. We take the integral from 0 to 6 of f of x, which equals x cubed over 3. And then I can evaluate that integral from 0 to 6. Okay? And the way that I would do that is what you do is you draw this little bar here and you put a 0 and a 6. Okay? And what you're going to do is find these two values. So what we do is we will plug in a 0 and see what we get. So 0 cubed is 0. 0 divided by 3 equals 0. And we will also plug in a 6. 6 cubed over 3. So what we have to do is say, what is 6? This is equal to 6 times 6 times 6 over 3. And if we don't want to use a calculator and we're prime factoring, we know that 6 is 3 times 2. So this is really equal to 3 times 2 times 3 times 2 times 3 times 2. And if you put all that over 3, you can cancel out the numerator and denominator, and now you're just left with 2 times 3 is 6, 6 times 2 is 12. 12 times 3 is 36. 36 times 2 is 72. Okay? So now you've evaluated the integral at 0 and at 72. And now we're going to take the absolute value of the difference between 0 and 72. So the absolute value, so 0 minus 72 is negative 72. Absolute value makes it positive. So the absolute value is 72. Now, if this had been in meters, let's say distance in meters, then you would put 72 meters squared. And that represents the area under the curve. Okay, so that represents the area in this green shaded region. So this is the area, and that's the power of this tool called an integral. It's a really amazing piece of technology. Okay? Maybe we should do another example. Let's do another example. And this time we will use a kind of like harder looking function. So in this example, we will consider the function f of x equals, and then let me just check something really quick. X squared minus 2x plus 1. Okay, so now we will consider the function x squared minus 2x plus 1. And we're going to do the same operation that we did before. And we'll look at what we can evaluate here in a second. But just before we begin, we'll just take a little graph of the function. So this is what the function looks like. It has its axis of symmetry at 1, and it sits on the x-axis, and it passes through a y-intercept at 1. So I can draw this in like this. Okay? Now, first we have to take the integral, and maybe we could say, I would like to know the area under this curve from 1 to 2. I want to know this area right here. I want to know this shaded region right here. What is the area of this shaded region? Again, a task that would be impossible to perform using conventional algebra and geometry. There's just no way because the line itself curves. And so we have to take the integral from 1 to 2 of f of x in order to find the area. So now we have to perform that integral math. So let me show you what that's going to look like. I'll write the original function and then we'll do some surgery on it. Now remember, when you're doing this, you have to add and divide in such a way that if you were to reverse the process, you would be back at your original function. Okay, so here I'm going to add 1 to the exponent and then divide by whatever that equals. So I'll divide by 2 plus 1, which is 3. Now, up here I had 1, it was just hidden, and I'll add 1 to it. And now I have x squared, you see? And in order to make sure that I cancel back to the original function if I were to take the derivative of that, I need to divide by whatever that is, 2. So divide by 1 plus 1, which is 2. Okay, so this one is x cubed divided by 3, and this is minus 2x squared divided by 2. Now what goes on over here? Here, this is a little bit of a new piece. Here, we're actually going to gain an x. So we're going to gain an x value. Because essentially there was an x sitting there with an exponent of 0, and we're adding 1 to it. Okay, so if you wanted to, you could say 0 plus 1 divided by 1. And there's that nice little harmony, 3, 2, 1. So let's clean this up and say the integral from 1 to 2 of f of x, we're still working on it, is equal to x cubed over 3. And then you notice that these 2's cancel, minus x squared plus, the 1's don't matter, plus x, and I don't have to write to the first power. So now my task is to evaluate the integral, for or from 1 to 2. That's what I've got to do. I've got to evaluate that integral from 1 to 2. And what that looks like is x cubed over 3 minus x squared plus x evaluated, this line here, from 1 to 2. And so this is pretty simple. We evaluate it first at 1, so I'll put in 1 cubed over 3 minus, open parentheses, 1 squared plus 1, and that will give me the evaluation of the integral at 1, and then I'll evaluate the integral at 2. So I'll put in here 2 cubed over 3 minus 2 squared plus 1, plus 2. Okay, let me make that clear. Plus 2. You're just replacing the x value with whatever number it is that you're evaluating it at. Okay, and let's see what that equals. We'll see what that equals. So first we'll take this one. 1 times 1 times 1 is 1 over 3, so I've got 1/3 minus 1 times 1 is 1, but I should put it in terms of 3, so we'll subtract out 3/3 to have a common denominator. Instead of writing 1, I know I'm going to have to subtract using common denominator, and then plus 1 in terms of 3, which is 3/3. So you see here that we have this little math problem right here. So we'll go from left to right. 1/3 minus 3/3 is negative 2/3. Negative 2/3 plus 3/3 is positive 1/3. So this just evaluates out to 1/3. Let's see what this one does. 2 times 2 is 4, times 2 is 8. So I have 8/3 minus 2 times 2 is 4. So if I wanted to write that in terms of 3, instead of writing 4, I'd write 12/3 plus 2. Again, I'd like to write 2 in terms of 3. So instead of writing a 2, I'll write 6/3, which is just 2. So this is just 4, and that's just 2. And so now we'll work left to right. Because we have common denominators, I have 8 minus 12, which is negative 4, plus 6, which is positive 2. So this equals positive 2/3. Okay, and now to finish the problem, I find the absolute difference, okay, the absolute difference between 1/3 and 2/3. Okay, so 1/3 minus 2/3 is negative 1/3, but the absolute difference is just 1/3. Okay, so if this was distance in, I don't know, centimeters, then the area under the curve would be 1/3 centimeters squared centimeters. Okay, and so there are right there 2 examples of how we can use integrals to actually find areas. And this is a brand new way to think about finding these areas now that we know about this new cool technology called integrals. Okay, so I hope you found that interesting. It's super useful, you know. So this is, if you ever wanted to know how do I find the area under a curved line, the way you find the area under the curved line is to take the integral of the function and then evaluate it over some distance. And you can choose what distance, or it'll be given to you to find. And this is calculus, you know. The integral helps me find the area under the curved line. And so this is what calculus looks like. And I hope that having watched this little tutorial, even if all of this seems very new to you, at the very least, you have seen it and you know the power that calculus can bring to your mathematics. And if that's all you gain from this video is kind of thinking, wow, I did not realize that such a thing was possible, then you and I had the same initial exposure experience with integrals, because when I first saw it, I said, well, I'll be darned. I didn't know it was possible. I would have never figured out how to do it on my own. And it took two amazing mathematicians, uh, Newton and Leibniz, to come up with this wonderful piece of technology called the integral. And it really works hand in hand with the derivative. But there it is. And I hope that you enjoyed it. Please make sure to like and subscribe if you have not already, and press the notification bell so you always are notified when I have a new video. Thank you.